Hello and thanks for watching. In this video we're going to go through some sequence theorems. So to start off with, let's have a theorem. Oh, apologies. Theorem. If xn is in the closed interval ab, then if xn converges to x, x is also in this closed interval ab, which intuitively makes sense because it's saying as we get really, really large, no matter how large we get, we're going to stay in this interval as long as we have a convergent sequence. And you might be thinking, okay, so why does it have to be a closed interval? Why can't it be an open interval? So now consider something like 1 over n, which is clearly between 1 and 0, right? But then, even though we never reach 0, we still go to 0. So we have to have this closed interval because we could converge it to one of the limit points. Okay, to start the proof, we're going to split this proof into two parts. So first, we're going to show that it has to be greater or equal to a, and then we'll show that it's less than or equal to b. So assume x is less than a. Since x is less than a, and we have for epsilon greater than 0, we have this being less than epsilon, but since it's less than a, then it's also less than xn. Therefore, we have xn minus x being less than epsilon. So now I'm going to choose epsilon. Since we can choose it from definition, I'll choose epsilon to be equal to a minus x over 2, which is greater than 0 since x is less than a. So it might seem like a very random epsilon, but we'll see that is actually, we'll see the motivation behind it in 1 second. So let's consider a minus xn. Now this is equal to a minus x plus x minus xn. We just added 0 here creatively, and we often do this in analysis, not just analysis, we do it in many fields, just so we can get a nicer result. And the reason why we did this was because we saw that we had this xn minus x, and we also, so we wanted to get the x in somewhere. Since we set this epsilon here, we wanted to get another x, so this means that this is greater than 2 epsilon, 2 epsilon minus epsilon, because this is 2 epsilon, but we also have this condition, xn minus x is less than epsilon, so we have that this whole thing, when we put them all together, is greater than 2 epsilon minus epsilon, which is equal to epsilon, which is greater than 0. But hang on, that means that xn is less than a, but xn, they're all within ab, so there's a contradiction here, which implies, so contradiction, so x has to be greater or equal to a. Okay, that's half of the proof done. Now we'll follow the other half in a really similar way. So instead, assume x is greater than b. So now how we had this time x is going to be greater than xn, so instead we have that x minus xn is less than epsilon. Now, proceeding in a similar way, let's consider xn minus b, which is equal to xn minus x plus x minus b. Now, we want to aim for a contradiction of sort again. So what if we set this equal to something, we set epsilon equal to something such that we can get this again, which would show that that xn is greater than b, which is not the case. So let's take some epsilon equal to x minus b, for example, which we have from here, and we have that this, or even over 2 even, and this is minus epsilon, and this is, well, this is less than, is it greater than minus epsilon, sorry, and this is 2 epsilon, which means that we have 2 epsilon minus epsilon again, which is equal to epsilon, which is greater than 0, of course. That means that b is less than xn, but then we have this again, which is a contradiction. So we have that x is less than or equal to b instead. And this is a closed interval, so that means that x has to be within, therefore, apologies for bad handwriting, x has to be in AB. And now we get some nice results directly from this. So for example, let's write a if I can write neatly, that is corollary. So if xn is less than yn and both converge, then the limit as n goes to infinity of xn is less than or equal to the limit as n goes to infinity of yn. Okay. Now, again, this should be quite obvious because every term is greater or equal to the term in the other sequence, so naturally you'd expect the limit to be greater or equal to as well. We can't make these inequalities strict for the same reason that we couldn't make them strict in here. That is because, for example, if we had say 1 over n and 2 over n, we know that one's going to be always greater than the other. However, they're both going to converge to 0, so we can't just exclude the possibility that they're equal. Okay, now we'll give a quick proof. So let's, for example, consider an equals yn minus xn, and from this we have that this is greater or equal to 0. Now the limit as n goes to infinity of an equals the limit as n goes to infinity of yn minus xn. However, from before, we had that this limit has to be since this is all greater than 0, then it also has to be greater than 0 from the theorem we just had before, which is greater than 0. But from our limit laws, we have that limit as n goes to infinity of yn minus, this is the same as this, which is greater than 0, so then it follows. Okay, nice. And we have one more final corollary, which in fact deserves its own name. We have the squeeze theorem as a direct consequence. So I'll write a theorem. Squeeze. Maybe I should have written it a bit closer, but it's fine. Squeeze theorem, which states that suppose xn is less than or equal to yn is less than or equal to zn, and the limit as n approaches infinity of xn is equal to the limit as n approaches infinity of zn. Then the limit as n approaches infinity of yn equals, let's say this is L, also equals L. Okay, and this is direct from the previous one, so we have that. The limit has to be between, between the other two limits from our previous corollary. So, but since those two are equal, we have that L is between, that the limit of yn as n goes to infinity is between L and L. However, this is the most important part, was to say that they must converge. But since yn converges and is between those, then the only possibility is that the limit as n goes to infinity of yn is also equal to L, because we only have one possible value for this, which also, I guess, seems quite obvious, but it's quite powerful. I'll give an example of where it could be used. So, for example, let's consider the limit as n goes to infinity of 2n over n factorial, which may seem nasty at first, but then we notice that all the terms are positive, so actually it's greater than 0, and we're just looking for some other limits to see that this actually goes to 0. So we can actually write 2 to the n over n factorial as 2 times 2 times 2 times over 1 over 2 over 3 and so on. But then we notice that other than this 2 here, all the terms here are less than or equal to 1. So actually this is bounded by 4 over n. So we can say that this is less than or equal to the limit as n goes to infinity of 4 over n. But then from limit laws, we know that this is 4 times the limit as n goes to infinity of 1 over n, and we proved that this goes to 0. So we know that, therefore, the limit of 2 to the n over n factorial is equal to 0 by squeeze theorem. Okay, that's all. I hope this video helped. Thanks for watching, and bye bye.